In this project, we'll be monitoring climatic variables influencing plant growth in a greenhouse using IoT, presenting you our overall circuitry, our actual circuitry. Here we have all the electronic components soldered onto a perf board, including DHT11 sensor, resistive soil moisture sensor, ESP32, our development board, the relay module, 12 volt DC solenoid valve, and a 12 volt DC fan. For creating the greenhouse replica, a corrugated box from scrap was taken and amputated to form the frame. Butter sheets were then used inside this frame to give transparent view of how a typical greenhouse would look like. On one side of the corrugated box, an aperture was made to fit the fan. The circuit was enclosed in a tinier box and kept inside this replica. This is how our actual prototype would look like. In order to create a final prototype, our overall system was divided into four main subsystems, namely the sensing system, the action system, the communication system, and power supply system. These can be further classified into various subsystems. Backend and automation. Here, the code is written in order to specify the operation to be performed. This generally cannot be accessed by the user, and this is the main program which we'll be loading onto our ESP32. Libraries like Wi-Fi library, asynchronous WebServer library, DHT11 library, SPIFFS library, followed by ESP32 library has been included since we are doing the backend and automation in Arduino IDE. Front-end design included creation of web page using HTML, CSS and JavaScript. HTML and CSS files were coded and saved separately in different files. JavaScript was enclosed in the HTML file itself under the script tag. Asynchronous JavaScript and XML, also known as AJAX, is a way to use JavaScript to talk to a web server, get back a response and update the web page without loading a new web page. Let us now go live to see how our web page would appear like without linking the backend files. If you closely observe, you can generally notice that the widgets are filled with parameters like percentage status temperature, percentage status threshold, percentage status moisture, and etc. These are the templates which has been created, and they appear like this because we haven't linked these files to the backend yet. Once we are done with linking these files to the backend, the templates would generally be replaced by the sensors or actuators data which is being sent in real time. Our ESP32 has an onboard flash memory of 4 MB. So before linking these files together, let us first store these programs in the flash memory, and in order to do that, let us save our HTML and CSS file in the folder named data inside the Arduino sketch folder. You can see over here that I've already created a folder named data, and this data folder contains both the CSS and HTML file separately. This is the SPIFFS file format which we are following in order to store data inside ESP32 flash memory. You can see this is the same website, but still this isn't linked to the backend. The program will be linked once we upload the sketch into our ESP32. So now let us upload the sketch data into ESP32 flash memory and load the program into ESP32. Before doing that, let us compile to check if there are any errors. Done compiling, so there are no errors. Let us go to Tools and select ESP32 sketch data upload. You can see SPIFFS uploading image is being shown over here. So what's basically happening over here is that we are storing our HTML and CSS file, which is there in the data folder, onto our ESP32 flash memory, which is of 4 MB. So SPIFFS image uploaded, and now let us upload the entire sketch into our ESP32 dev board. Make sure you have selected the right port and also the right board. In our case, we are using a ESP32 Vroom32D. So let us wait until the program gets loaded into ESP32. Done uploading. So let us now open our serial monitor, and once uploaded, just press on reset button on ESP32. So we now get the IP address, that is 192.168.1.104. Let us now input this IP address in a new web browser, 192.168.1.104. So here it is. You can still see values like nan and some random values being displayed in the widgets because we haven't yet built our circuitry with the ESP32. So now let us do that. The sensors used are DHT11 and resistive soil moisture sensor. The actuators used are 12 volt DC rotary fan, 12 volt DC solenoid valve, and a 4 channel 12 volt relay module with optocoupler. The microcontroller used is ESP32 Vroom32D. We are powering our project by a 12 volt 2 amps adapter, and we also use a 5 volt voltage regulator to power ESP32 from the same source. This is how our final circuit diagram would look like. So once we are done with our circuit connections, let us power on our circuit and input the IP address which we got before. You can note over here that the widgets are filled with data which is being sent from the sensor, and previously they were filled with templates, and now they are being replaced by the real-time data which is being sent from the sensors to the ESP server, and they have been updated respectively in the web page. You can see over here that the fan is turned on and the water valve or the solenoid is turned off. The same status is being indicated in the status menu. Our web page is divided into 3 sections as shown in the navigation bar. The current status section contains 6 widgets which shows real-time values of temperature, humidity, moisture, and also the status of cooling fan and irrigation. The set threshold section consists of 2 widgets which help us to set threshold values for temperature and moisture. The manual control section helps us to manually turn on the cooling fan and water. The current status of fan is turned on, so let us set a threshold value for it. The current temperature is 26 degrees, so let us set the temperature threshold to be 35 degrees and update the value. You see that the cooling fan is turned off now, and the same is indicated in the cooling fan status widget as well. This is because the current temperature is well below the current temperature threshold which is being set. There has been a slight bug in the cooling fan on. You can see the cooling fan status is also turned off. Let us turn on the cooling fan manually now and hit save. The cooling fan is turned on now, and the same will be indicated in the status section as well. The irrigation is turned off. Let us turn on irrigation manually now. You see that both the cooling fan and irrigation is turned on now. The logic is built in such a way that both of these actuators will turn off exactly after 1 minute from they being turned on. So we'll have to wait for a period of 60 seconds for these actuators to turn off, and it can be modified to how much ever time we want. Web page is made user responsive with the use of media query.